Okay, so hi guys, in this video lecture we will be talking about how to find the total number of stereoisomers of a given compound. Okay, so let me define the headline. So how to find total number of stereoisomers of a given compound. Okay, so by stereoisomers I mean optical and geometrical, though both. So if we have a compounds like this, so the total number of stereoisomers for this compound would be 2, one R and another S. Both would be optical, no geometrical. Okay, for the second case I have CS3 here. Let me draw the mirror image of the same. So this would be one. Another pair can be this one, where we have VRH here and CLH here. If you draw the mirror image of this compound, you would get something like BRH and HCl with 2CH3 here. Okay, so as you can see, means this compound and the remaining two, and this compound and the remaining two will be diastereomers, but the pair would be enantiomers. So stereoisomer in this case would be 4. Oh, all are optical isomers. Okay, so how many stereoisomers are there in this compound? Obviously 2. Why? We can have just two geometrical isomers. What about this compound? We have Cl here. Okay, so as you can see, this is the first stereocenter and this is the second stereocenter. So we would have total stereoisomers as 4, 2 optical and 2 geometrical. So R cis, R trans, S cis, S trans, these 4 would be there. Okay, so the general formula we can deduce for actually calculating the total number of stereoisomers is as you can guess from the previous example, is 2 to the power n, where obviously n would be 1 for alkene chiral center or asymmetrical alkene. So n would be for alkene chiral center or unsymmetrical alkene. Okay, so then let's say we have an example in which we have to calculate total number of stereoisomers of this compound. CS3H this. Okay, so this would be considered one stereogenic area. This is the cumulene. We have discussed it previously also. CS3H and CS3H. Okay, so obviously this would be R, then this would be S. So I hope you are as there are even number of bonds in this cumulene, I guess you can imagine that these CS3 and H would be in plus Z minus Z, while this CS3H would be in the same plane as the cumulene, or the three carbons of cumulene. Okay, So this is R, this would be S, and the total number of stereoisomers would be 2. Oh, am I missing something? No. Why? Because if you see this compound, this would be more of a coming out of the plane, or the upper, not coming out of the plane, but I drew it wrong. Not coming out of the plane, but it would be um, in some plus z, and h would be in minus z. Similarly, this would be in plus z and this would be in minus z, right? So if you actually want, if you have to, if you have a doubt that aren't they identical when I rotate this by 180 degree, so this CH3, this H, and this CH3 and this H are in plane. So if you rotate it by 180 degree, so what would actually happen is this H and this H would come in plus Z, and this CH3 would come in go in minus Z. So these two compounds will not be superimposable, and this is R and this would be S. Okay, let us take another example. We are attached here and we have this. So how many stereoisomers would be there for this compound? So as you can see that this is a chiral center. We just discussed the stereoisomers of biphenyl in some previous last 2-3 videos. This is a chiral center. Okay, let me draw it in. This is a chiral center. This is sorry, not a chiral center. This is a stereo center. This is a stereo center. And what is the other stereo center? This is the stereo center. So total number of stereoisomers is 2 to the power 3, which is 8. Okay, so now let's talk about the general form of formula. When is the 2 to the power n formula valid, and what are the special cases that needs to be handled and taken care of? So let's talk about the general formula. So if we have something like the total number of stereoisomers would be 2 to the power n, where n is a number of chiral center, or okay, let me write it down only, where n can be number of chiral center or it can be number of alkene which will show geometrical isomerism, number of alkene which can show geometrical isomerism. Third, it can be number of allene which is unsymmetrical, number of allene which are better asymmetrical, or it can be number of biphenyl which is unsymmetrical, number of biphenyl which are unsymmetrical, number of spiro which are unsymmetrical, number of spiro which are unsymmetrical, and or the number of allene, number of alkene which can show geometrical isomerism is already covered. So number of cumulines which can show geometrical isomerism, or so number of cumulines which can show geometrical isomerism. Okay, so you have to remember whether the number of bonds in cumulees are even or not for the case to hold true. Okay, so now let us look at some of the examples or cases first. So when compound is symmetrical and there are even number of chiral center in the compound. So case is when compound is symmetrical with even number of chiral center. Okay, so let's have a look at this. So in this case the compound is symmetrical and the POS can be found. This is the POS. Okay, so if we draw the mirror image of this, we would get something like this, which would be identically same to the first compound, and this is identical, so we will rule it out. What else can be drawn from this structure? We can have something like this, which will be an enantiomer. If we draw a mirror, then these two are not superimposable. Okay, hence the total number of optically active isomers. So optically active isomers, I can write them to be 2 to the power n minus 1, and meso compounds would be 2 to the power n by 2 minus 1. Okay, let me write it as A, which denotes actively active, and M, which denotes meso compounds. So total number of stereoisomers which are optically active and inactive would be A plus M. Okay, so now let's look at a different case, or case 2, wherein when compound is symmetrical and having odd number of chiral centers. So second condition is when what happens if a compound is asymmetrical? Then obviously the formula was 2 to the power n. We now are considering the case when compound is symmetrical but the total number of chiral centers are even or odd. So when compound is symmetrical and having odd number of chiral center. So if we have some things like HOH, CO2H. Now in this example the middle carbon is not chiral. Why? Because the groups above and below in this representation are same, hence if two groups are same it would be a chiral carbon atom. Okay, so in this case if we actually change the, let it be CH3 for the time being, doesn't matter. Okay, so if we actually change the position of H and OH here to suit something like this, CH3 and CH3, then the mirror image formed would actually be an enantiomer, and these two compounds would not be identical to each other. OHH, HOH, OHH and CH3. And what else? We can also draw a compound like this, OH, HH, OH, OH here. Okay, so this compound is actually a meso compound. Okay, so, and this also was a meso compound, but this was a enantiomer or chiral compounds. Okay, so in this case what we have is active is, that means A is 2 to the power n minus 1 minus 2 to the power n by 2 minus 1, this is A, and meso is 2 to the power n by 2 minus 1, this is M. Okay, so please remember this formula, that if the compound is symmetrical and it has 3 chiral centers, then this would be the, or total number of stereoisomers is obviously A plus M. This formula would be used if the compound is symmetrical and is having even number of chiral centers, then this formula would be used, where optically active isomers are 2 to the power n minus 1 and meso compounds are 2 to the power n by 2 minus 1. Okay, so this brings us to the end of this lecture. In the next lecture, we'll be seeing some of the examples of calculation of total number of stereoisomers of the following compounds. So till then, good luck and goodbye.